Hello, everyone. I'm Jatin, and she is Bailey, and we are working on this project called Privacy Promoting Fake News Detection. Detecting fake news is an important problem because if you look at an article, you want to know whether it's fake or not because you base your decision on the articles you look at, and if you believe something is real, it's going to influence a lot of decisions in your life. So various platforms are trying to build fake news detectors. There are various research groups that are working on this, and they're creating new models, new ML techniques, new data sets to show how difficult the problem is. And so essentially, fake news detection is an important problem. But fundamentally, the detection part requires user data. And that is a privacy concern because we don't want Facebook or Twitter to be collecting user data and not and doing whatever they do with it. We don't want that. So we want to detect fake news in a way which is privacy promoting, meaning the platform never sees the user data. That's our goal. And the big hammer and the technique we use to basically achieve that is called federated learning. The idea is that each individual user trains its own model using its own user data, and then it sends the model to the platform, and the platform combines it in some way to create the global model. The essential point is user data never leaves the user device, and that's why it's privacy promoting. The key research question that we want to answer in our presentation, in our project, is can fake news detection be done in a low bandwidth setting with federated learning? The low bandwidth setting is another axis which is kind of difficult to overcome because user devices are subject to various connectivity constraints which we want to model. So there are two difficulties, low bandwidth and federated learning. And we want to see if we can handle both of them without losing much in performance. So let me take you through in a bit more detail about what our architecture and models look like. So we have the platform, we have user devices. Finally, we have this third entity called the labeler. The platform stores the global model, which is like a logistic regressor. Think of it like a linear classifier with some fancy activation function. The user model goes like this. So the user sees posts, and what every user has access to is the expert labeler. The users can send some post for veracity confirmation to the expert, and the expert replies whether or not a particular piece of article is fake or not. Now, if every user sends every post they see to the expert labeler, this is going to be a lot of manual work, which is not realistic. So what we do is we select certain few posts. Each user selects certain few posts and only sends those to the labeler. And we have various query rules in deciding how the post is going to get selected. Now, the user sends some posts to the experts, receive feedback, and then that feedback is used to train the user model because that acts as the training data. The user model trains itself on the training data and eventually sends it back to the global model, to the platform, which makes a global model out of it. The way we combine these or compile these various user models into a final global model is using federated averaging. We essentially take the weights of the user models, average them, and create the global model. Now, to evaluate this architecture, we procured a data set, which is called Fake News Net. It was published in 2018. It has approximately 20K posts. Each post is like an article, and it has a label whether or not it's real or fake. We do some pre-processing techniques on it. We use classic NLP techniques called stemming, noise removal, TF-IDF. What this pre-processing essentially does is it looks at each article, looks at the words, looks at their frequency, and translates each word to a weight, like how important a particular word is to an article. So it translates the textual representation of the article to a numeric one, which we can then feed to a model. There's one more pre-processing step that we do. It's called downsampling. So in the data set that we picked, the ratio of real and fake news was 50% or 1-to-1. But this is not realistic, we felt, because in real life you would have much more real articles than fake articles. So in order to simulate that, what we did was we downsampled some fake posts. We removed some fake posts from the data set, essentially. And we had a data set of lesser number of posts, but with a higher ratio of real to fake. Now, you take all the data set, you do the pre-processing, convert the thing into features, then you get your training data. And then the way we simulate users is at each time step, every user samples some post uniformly randomly from this data set, and then it sees a bunch of posts, and every so often it sends, using a query rule, the post to the expert labeler, which says whether or not this article is fake or real. And that's why, and we train our user model, each individual user model using that data, and finally send it to the global model at an epoch of length t. And Bailey will talk more about what the epochs are for our evaluation. Then we test our global model on the test data using this metric called AUC-ROC. Think of AUC-ROC like accuracy, but like more robust because it checks the model at various thresholds.
Okay, thanks, Jatin. Okay, so now I'll tell you a little bit more about this evaluation step here. So at every epoch, which in this case is every 200 time steps, we are retraining our user models, updating our global model, and then evaluating that global model to see what its performance is. And so this simulation is like quite complicated, and there are several parameters that we have to set. So I'll just tell you the parameter settings, and if you're curious, we can talk through like the supplemental information about how we chose those. But in our simulation, we assume that there are 50 users using the platform. They can send at most 5 posts to the expert every epoch. The ratio of fake to real articles is 1 to 80. The length of an epoch is 200 time steps, which means that the model is updated every 200 posts seen by users. And then the base data, which is the data set used to train the original user models prior to any like simulation, is 25 posts in size. So the model that we're really interested in testing, if you recall our research question, is a low bandwidth federated model. So here we have a table of the parameters of the different benchmarks that we consider. And here is the location of the federated low bandwidth model that we're interested in talking about. And so we consider 2 versions of this model with 2 different query rules. I'll gloss over these details for now. But basically what we compare this federated model to primarily is the standard model, which is if the federated model receives these user models and aggregates them, the standard model takes the union of all the data available to these user models and directly trains a model. And so this gap, we call it the federation gap, which is the cost of having to do federation essentially in the interest of privacy. The next benchmark we consider is a benchmark that measures the cost of this low bandwidth constraint, where we can send very few posts to the expert. And so what we see here is we have 2 models, one federated, one not, but which have unlimited bandwidth, which means that the user can query the expert as many times as it wants, so it can ask for labels on every post that the user sees. And then finally, we consider the best possible model, which is just a model directly trained on the entire training set. And so in our demo, which we'll show you, we show you the results of 2 models, and you can plug in your own fake news data. You can also use some of the examples we've provided. But in these, we basically show the models that you see starred here, and they are the federated low bandwidth models trained for 15 epochs, and they use the top K query rule, which basically means that the user models are choosing to send the posts that are most likely to be fake to the expert when they have the opportunity. And so the important points of this plot really to think about are the gaps between the dashed lines and the solid lines, and then also the colored lines versus the gray lines. So the gap between the dashed lines and the solid lines represent the federation gap, because dashed lines represent federated models, and their corresponding solid lines represent the corresponding non-federated model. And so the federation gaps range, as they're listed here, between like 1% and 3%, so very small. And then you also see pretty small gaps between the colored models and the gray models, which indicates that the low bandwidth requirement actually doesn't have a really big impact on performance. And you see that in both models. They only differ really in the sense that this one doesn't allow access to proper nouns when we do the pre-processing, whereas here it does allow access to proper nouns. So, we have these predictions, but we kind of want to know where they come from. And so as part of our demo and also in this poster, we show a word cloud that demonstrates which words are most closely associated with fake and real news. Yellow are fake and purple are real. And what you see, I think, kind of the most interesting takeaway is that fake news tends to be really associated with words that you see a lot in clickbait, like source, insider, exclusively, and then also words like reportedly, and essentially an according, where the fake news is trying to essentially kind of like outsource blame for these claims to like other outlets and kind of saying we're just re-reporting information. And so we'll see a little bit more of this in the demo. But anyway, just to recap the kind of future work on this project, the model of the platform, although like pretty complicated, is a bit rudimentary in the sense that posts are uniformly sampled when we're choosing posts for users to see, which is probably unrealistic because of content curation algorithms. Also, we want to increase the sophistication of the pre-processing, for example, considering strings of words rather than just single words. And then also, this is only in one data set in one model, so it'd be nice to expand the investigation to other data sets and models. So now we can move to the demo. All right, so we'll just demo a few examples of real and fake news sources. And so what you're looking at here is a platform where you can enter something that you make up or some text from an existing article, and we'll run both our model with and without proper nouns on it. And we'll also show you this explainability graphic and to explain why the prediction was made. So we'll start with like a pretty classic example of real news, which is from the New York Times yesterday. The Pentagon chief ordering a new inquiry into the US airstrike. So I'm just going to take this text, and I could take some or all of it, it doesn't really matter. And I'm going to paste it into the box. And so we're hoping that this says real. I know, it takes a little bit to run because it's really long. Okay, so what we see is we have two models, and our model with proper nouns classifies this as real, although it's not super sure. And then our without proper nouns says it's inconclusive. And so I'll draw your attention to the reasons for it making that prediction. The word report and reports tends to be associated with fake news pretty often. It's shown in yellow and very large. That's signifying its importance. But you also have a lot of purple words which are associated with real news, things like announced, services, allegations, like kind of informational words. And you'll start to see more patterns that are more obvious in the other examples.
Okay, that was a real article. Let's see a fake one and what it looks like. So one of my favorites is that they created a fake article which says Jeb Bush reportedly enters mental hospital. So let's just paste that in there and feed it to the model. Okay, so the model with proper nouns is able to show with a high accuracy, with a high confidence score, that the article is fake. And the model without proper nouns is inconclusive again. And this is basically because the model with proper nouns has access to things like Donald and Trump, which is like a very big indicator because in our data set, for example, Donald Trump was related to a lot of fake articles. The model without the proper nouns, however, only has access to Trump. And this is unfortunate because Trump is also like a real word, so our model is not able to filter it out before, like at the pre-processing step when we remove proper nouns. But other than that, it's not. It doesn't have like Donald, for example. And another thing that I want to mention is essentially the thing reportedly that Bailey mentioned, and like calling, which is like words which hedge and like ascribe or like shy away from taking responsibility. These kind of things are usually associated with fake news, and like they get higher scores when the model is deciding whether the news is real or fake.